we explored diversification processes, such as the pure birth process, or Yule process, and the birth-death process. And we established that the pure birth process is governed by only a single parameter, the speciation rate, lambda, and the birth-death process is governed by two parameters, speciation, lambda, and extinction, mu. And what we then looked at is how different patterns of how these parameters are distributed, how they affect tree shapes. So, for example, we looked at the tendency of nodes to cluster more towards the root or more towards the present, respectively suggesting higher diversification nearer the root or nearer to the present. And there was even a metric for that, the gamma metric of Pybus et al., which might be one way to detect, let's say, a deviation of rate constancy across the tree. So that would be then changes through time. So, for example, if nodes cluster closer to the root than you would expect under the null model, well, then maybe there's higher diversification earlier on, and then it kind of attenuates as you get closer to the present. But what we also looked at is that maybe diversification could be unevenly distributed across lineages, such that you get trees that are more asymmetrical than we would expect under the null models. And we also saw that there were some metrics for that. But wouldn't it be nice if we actually had not just these hypothetical lambda and mu parameters, but if we could actually estimate them? Here now we are going to look at a couple of different contexts within which you might estimate these parameters. So the method that is more often than not used and referred to in the literature is the method of Ni et al. 1994, which gives us two maximum likelihood estimates, one for the what's called the turnover, which is extinction over speciation, or mu over lambda, and the net diversification rate, which is lambda minus mu, speciation minus extinction. And there's a couple of different R packages that allow us to estimate these. So in this mini lecture, we're also going to see a little bit of R codes. I think it's going to be pretty straightforward. So let's not be intimidated by this, but if you really cannot follow along, then that is a very serious red flag that you need to pay a lot of attention in the upcoming R refresher, because we're aiming at least this level. So let's jump right in. Here we are using a package called ape, which we are loading. We are then reading a tree. So the tree file is called phytophilo.tree, which is a very large plant phylogeny. It's in a Newick format, and once we've read it in, we have a phi object, which is a tree that has branch lengths and tips with names. That tree we would like to use as input to estimate these birth-death parameters. However, the tree is slightly misbehaved, firstly because it is not quite ultrametric. I mean, it is intended to be ultrametric, but the tips don't exactly line up with the kind of precision that R would like to see. So here we're forcing the tree into being ultrametric by extending all the terminal branches that are not quite lining up at present. So this is a little cheeky, I can just get away with this because I know that the tree is basically ultrametric. There's just a little bit of a rounding error that R is unhappy about. Secondly, we need to make this tree binary. So if there's any polytomies, then the method of Ni et al. Is going to be very unhappy about that because it kind of suggests that there's instantaneous multi-way speciation, and here in this framework we're not dealing with in those. So the tree is also forced to become binary by just randomly resolving polytomies and inserting very short branches. That's the multi2di function call. Okay, then we have pre-prepared our tree, the bin ultra object, and we use that as the input for the birth-death function call, and then we get a result. So here the result is printed out to the R terminal, and we get our estimates for the turnover here, and for the net speciation rate we get estimates for the standard error, so we are also here provided with the confidence intervals. Now there's other ways also to arrive at estimates for lambda and mu. So if you're more a phytools gal or guy, then you can also use that package here. And then other than that, the pre-processing is the same. They also operate on the same tree objects, so there's just compatibility between these packages. And then we can provide the pre-processed tree as the input for the function call, which in phytools is called fit.bd, birth-death. That result gives us direct estimates, so we don't get turnover and net diversification rate. It gives us directly lambda and mu. So just as a quick sanity check, it might be interesting to see if these packages give us the same results. So firstly, the log likelihoods are more or less the same. Again, you can see that the precision differs a little bit, but okay. And here we have the turnover that Ape estimated, and here we can just use these two lambda and mu parameters ourselves to calculate this turnover. We see that this is, again, basically the same value, and we see that also in the net diversification rate. So here we calculate what that is, and we get basically the same value. Okay, very cool. So now we have a single point estimate of speciation and extinction, and we assume that this just applies uniformly across the tree. However, maybe that's not the case. So the first thing that we might do to check it out is to plot a lineage through time plot, or an LTT plot. So that's what we're doing here. And then what R would spit out is this. So here you can see that this is indeed a very large tree. The phyllo tree is for all the flowering plants. And so you can see that we're going well over 100,000 tips. You can see that indeed this is a log scale. And here we see time working its way towards the present. And when we look at the plot, well, it doesn't look all that linear, does it? Like, it's for a long while, it seems to be going linearly, but here it appears that there's some kind of acceleration. So could we investigate that? Well, yes, we can. At least ever since 2011, when Tanja Stadler developed a method for looking at rate shifts through time. So here's the general idea. There might be epochs in time, in the history of life on Earth, where basically for everything that was alive at that time, circumstances were different. And maybe they were different because they were more crappy, an ice age or something. Or maybe they were different because they were kind of more pleasant, maybe a little warmer or whatever, right? Anyway, so just for everybody alive at the time, situation had changed. And then what the technique does here is it requires you to basically establish the boundaries between these different epochs. So in this example that is plotted here, we are seeing 3 different windows. Here there's the window above this line, so the oldest window, and then we have one in the middle, and then we have one that is working its way towards the present. And you can see here that there are different lambdas and mu's for these different windows, right? So now we're moving towards a kind of concept where we have these parameters, but we have different versions for them depending on the context. In this case, different time windows. So we then we figure out what our epochs are or our time windows, and then through some very, very clever calculations, it is going to figure out whether there are any rate shifts from one window to another. So here, yet another R package gets involved, the tree-par package. Again, we are reading in our great big tree. We are pre-processing it, and we are also, as I forgot to mention, it says here, we also have to specify how complete our tree is. So, this is these are the taxa that made it to the present, but it might be that from among these we are missing some of them. So, for example, we might have 95% of all the flowering plants in our tree, but not entirely 100%. And what this method would like to know is, what fraction we think we're having. So here we specify, well, it's we think we are only missing 5%. Okay, then we have to set up basically the grid or these epochs. So we say, well, we have a total time span of 400 million years from start to finish, and we want to split that up in a grid of 100 million years at every step. Then here there's a little magic that needs to happen to create some kind of input object. But here is where the magic actually happens. Here we are going to calculate the maximum likelihood estimate for the number of birth-death rate shifts. All right, so it spins its wheels. When you actually do this in RStudio, it'll take a minute. And then what you get back in your result object is a really gnarly kind of nested array. So you have to really look in the manual to figure out where what is. But somewhere within this mountain of numbers are the things that we're interested in. Namely, we are interested in here what the maximum likelihood estimate is for in which window a single rate shift took place, and that is the estimate for the most recent window of 100 million years, as this result points out. And then what it gives us is the diversification rate before that shift, and then we can also get the rate after that shift, and you can see that this is a smaller number than this. In other words, the diversification rate was lower before that most recent rate shift, and then it became higher. Well, that is also what our LTT plot is suggesting. So, so far this makes sense. Is that maximum likelihood estimate of a single rate shift actually significant? So here what we're doing is a likelihood ratio test. This is also not new to us yet. like we've seen that before. We have two likelihoods, and this one was buried inside the array over here, and this one was buried a little bit elsewhere. And then what we do is we take the difference between those likelihoods, multiply by 2, and then by sheer magic we can use that as a test statistic within a chi-square testing framework. We need to take into account what our degrees of freedom are, which is the number of free parameters in the model. And then, well, we get our result back. So in this case, the result is indeed significant. So for example, if we compare that with the possibility of 2 rate shifts, which are kind of buried somewhere else in the array, well, then that is actually not significant. So what our LTT plot showed us is also what the test here demonstrates, which is that the diversification rate is higher in the most recent, let's say, 100 million years, and even significantly so. So that's kind of neat, and you know, this is all not a huge discovery, because when we look at, for example, this figure here, which shows the diversification of the flowering plants through time, we see that indeed during the Cenozoic there's a great big increase in the number of lineages. So we have just shown to ourselves something that we could have already known, but it's nice that the tree actually behaves as it should, and it's showing us. So here what we were investigating is the scenario where we assume that these changes in the diversification rate are basically extrinsic in relation to the lineages. I mean, they're traveling through time, and then without their involvement, circumstances have changed, and so they diversify more quickly or more slowly. But just to wrap it up real quick, just attract your attention to something else, that sometimes the lineages themselves could be causing changes in diversification, which is basically one way to set up the next lectures where we investigate that more deeply. Now this is kind of a special case. Here we see on the left a lineage through time plot, and by now we can probably detect that this is not linear, because this is what it would have been. Obviously it's bulging towards the past. And here the argument that the authors make in their paper is that this is because of these birds themselves. It's their own fault, because, well, first there were very few of them, and that was great, because then they could all become new species. Yay, there's lots of room. But then as time progresses and the number of lineages started accumulating, well, maybe they got a little bit in each other's way or something, but anyhow, they were causing the decline in their own diversification rate. So this is basically density dependent.